Our main objective of the final project was to use dynamic programming in MIPS to create two functions, namely malloc and free. Malloc, when given a size block, returns a pointer to the head of a stack with the certain given size block. Free deallocates this memory given the pointer to the head if the pointer exists. To achieve these goals, we created two sprints, sprint 1 and sprint 2, one for each week of the project that we had, and we divided tasks among each sprints and each team members. During sprint 1, we did extensive research on malloc and MIPS and how they work. We also went ahead and implemented malloc and free in MIPS so that we could actually understand how the code worked and its inner intricacies. Also, we learned how to use the Mars simulator. There were a few tasks that were partially completed, such as implementing our C code of malloc and MIPS, malloc and free in MIPS. So these partially completed tasks were moved to sprint 2. During sprint 2, we had tasks such as the backlog task from sprint 1, and to implement a linked list and to use our malloc and free written in MIPS to assign memory to this linked list. We used SRBK and other required functions to make sure that the linked list works correctly, and we also wrote test cases for our MIPS code to test if the allocation and deallocation of memory works as we expected it to be.
In the beginning of the project, there were several goals that we set for ourselves. They are as follows. Implementing malloc in C. In order to begin coding malloc in MIPS, we figured out that first, we had to understand and write the malloc code in C. We did intensive research on this subject and came up with a working malloc algorithm in C about which we will explain later in the video. Implementing free in C. Similar to the requirements for writing malloc in MIPS, we had to figure out the free code in C. For this purpose, we used the inbuilt free function. Implementing linked list in C. One major aspect of this project was to implement a linked list data structure to take note of the memory usage and memory locations used for storing data. We chose a linked list over other data structures like array because of its efficiency and easy removal of nodes from the linked list. Creating the Scrum 1 report. Although we couldn't finish all of our declared plans for the Scrum 1, we did succeed in major areas including the research of malloc, free and linked list implementation in C, and a minor implementation of malloc in MIPS. We also taught ourselves how to use the Mars simulator and count instruction for checking efficiency of our code. Planning for Scrum 2. For Scrum 2, we planned on implementing the malloc, free and linked list in MIPS as well as finishing other partially completed tasks from Scrum 1. Although we initially planned on implementing a single linked list, we used a doubly linked list with previous and next pointer instead due to its efficiency and ease in implementation. Translating C code into MIPS. To implement malloc and free in MIPS, we created a basic linked list where we get the input data from the user. To store that data, we use malloc, and for the deletion of node, we created a free function. We will explain about this and the code testing part later in this video.
Here, we can see a basic implementation of malloc in C. We did a lot of research before writing the code for malloc. As we all know, malloc function allocates the requested memory block in heap for use. Well, it dynamically allocates required memory to store our nodes in this case. We use the S break to request for the required size. Size t here in our code is basically a node type. The first thing we do is point to the starting address using the void pointer. After that, we request for a certain amount of memory that in our case is required size. And if everything goes well, our malloc function returns the first address of our requested size. We then use that requested size to build our linked list. In our case, we've had two functions in our linked list, add memory and free memory. When we do add memory, we call malloc every time to separate out the size for our nodes and then create a linked list as we do in C. For our free function, we were unable to make a free function, so we used the inbuilt free function to delete head and current node pointers that we made to free up memory from the heap. We call all these functions from inside our main, and this is how our malloc looks in C. Here, we can see the code for the implementation of malloc and free in MIPS using a linked list. At first, I have described some placeholders such as please insert the number or such things, which I will call later for my use. Running over the code now, we have to first assume that throughout this code, S1 will be my head pointer and S2 will be my current pointer. Now, starting with the code, we basically take input from the user for the data that we will be storing in our linked list. Our data type is integer, so hence, we separated out 12 bytes of memory, 4 for previous address, 4 for the next address, and 4 to store our integer. We implemented 4 functions in the linked list. Add elements, which calls the malloc function every time to allocate some size to our node pointer that we will add to our linked list. A function to delete the current node, which is not fully functional as of now, but we plan on improving it later. We also have another function named the go to next node, which just helps us traverse through the nodes. And our last function is go to head function, which helps us take our current pointer back to the head to make changes in our linked list. Running over all the code now, as we can see here, our main function basically gives the user some choices and acts upon what the user chooses. Now, going to jump to object function, this function just jumps to another function that the user opts for. The goToNext function is basically a function that traverses through our linked list. In this function, we check if the head of the linked list is 0. If it is, then we just go back to the main function, because we know that if the head is null, then there is no element in the linked list. If not, then we check that if we've reached the end of the linked list. In that case as well, we jump back to the main function because we know that there won't be any element after that. If either of those cases are false, then we just traverse through the linked list in such a way that we store the current pointer's next address to a temporary pointer and print out the value of the temporary pointer. After that, we store the temporary pointer's address to current address in such a way that current is now changed to the next of current. The other function that we have is goToHead, which basically moves my current pointer to the head pointer in such a way that now my current points to the head. My addElement function checks for three things. If the linked list has already been allocated. The second thing that it checks for is if we are adding it to the end of the linked list, or if we are adding it in between. Every time I call my addElement function, we allocate some size for our node, specifically 12 bytes. And as I explained, 4 bytes for previous, 4 bytes for next, and 4 bytes to store our integer. At first, we automatically allocate the next and previous to nulls for easier calculations later. In our data, we store the integer value that we get from the user. After that, what we basically do is, if we have already allocated a pointer, that is, if we already have a head, then whatever our current value stores, we just point the current's next to head, the temporary pointer that we just created. Else, if we have not created head, then what we do is we assign the temporary pointer to the head pointer and point both current and temporary to head. The other function that I have is print everything, which is basically a helper function that helps me print everything without having to call syscalls over and over again. The allocate size is basically a malloc function that just allocates 12 bytes of memory to each node that I create. The delete element loop is also another helper function that helps the delete feature work. The delete element, it has some basic functionality such as deleting current node. If the linked list doesn't contain any element, then we just go back to the start of the linked list. I also created two edge cases for this. Once when we delete from the head, and to see if we delete from the tail. If we're deleting from the head, then what we have to do is assign a new head that will be the next of the head. And if we're deleting from the tail, then what we do is assign a new tail that is the previous from the tail that we have right now. Else, if we're deleting between two nodes, then what we do is assign the current next node to the next previous node. And that way we just break the link between two nodes. That is basically our implementation of malloc in linked list. We can just run our code once and see what it looks like. So basically, it asks user for some choices. So now, if I do one, that is addElement, it asks me for a number. So say I insert 10. Now, you can see how my memory began from 600, and my current element in the node is 10. Now, if I add one more element, then let's say I insert 20, and you can see how my current address is increased by 12, because we separated out 12 bytes for every node that we have, and my current element reaches to 20. Now, if I keep adding elements, it just keeps increasing by 12 each time. Now, my goToNext function, if I call it right now, then it'll just go back to the loop because my current has no next since it's in the tail. Now, if I go to head, then as you can see, it jumps back to head, giving me the same address the head has and the same element that head has. Now, I can traverse through it if I choose to, that is, if I press 3 and press enter, you can see that I go to the next node in the linked list. Now, the final thing is I can also add in between elements, that is like right now. If I just insert 20, then it just adds a new element in between my first and my second node. So that is the basic implementation of linked list that we have as of now.
We ran our code and tried using all the input methods. GoToNext node works well until we reach the last node when it throws it off. And we are still trying to overcome that error, but apart from that, our GoToNext node works well in all other cases. Till now, we have fully functional addElement, which uses the implementation of malloc and assigns new element to the newly allocated space. Our delete element is error prone, as you can see. We couldn't implement the free feature, as we plan to improve it in the future.